Today we're going to talk about modeling with exponential growth and decay, and our first problem says that the bacteria count in a heated swimming pool is 1,500 bacteria per cubic centimeter on Monday morning at 8 a.m., and the count doubles every day thereafter. And our first question says, what bacteria count can you expect on Wednesday at 8 a.m.? Well, let's fill in our table in problem number 2 before we figure out our bacteria count on Wednesday at 8 a.m. So when we started here, we started with the bacteria of 1,500. Remember what it says. It doubles every day. So if we double 1,500, we get 3,000. If we double 3,000, we get 6,000. If we double 6,000, we get 12,000. If we double 12,000, we get 24,000. And if we double 24,000, we get 48,000. And something maybe that would be helpful for you, that's helpful for me, is let's look at our days here. This is Monday, Tuesday, Wednesday, Thursday, Friday, Saturday. And just as an aside, those of us who are retired swimmers or even current swimmers, that's what chlorine is for, because we don't like a lot of bacteria in the pool. But what we're looking at here is what bacteria count can you expect on Wednesday at 8 a.m.? Well, Monday at 8 a.m. is 1,500. Tuesday at 8 a.m. it's 3,000. So on Wednesday at 8 a.m. we've got 6,000 bacteria. But suppose we want to know what the bacteria is on Thursday at 2 p.m. And that is approximately 3.25 days after the initial count. So I was thinking of one way to do this problem, but all of a sudden I want to check a different way, and maybe you have an approximation that you're thinking. Any thoughts on, or any guesses on how much about do you think we'd have at Thursday at 2 o'clock? John? 15,000. I thought the same thing. The 15,000. What we were thinking is that on Thursday in the morning, we had 12,000 bacteria. Thursday at 8 a.m. But then we've got 0.25 days. So if we multiply that by 0.25, that gives us about 3,000, not even about, gives us 3,000. And then if we add the 12,000 back in, there's where the 15,000 bacteria come into play. And I know I explained in math instead of words, but I think that'll be more understandable, at least I hope so. Well, we could answer this a little bit more precisely. That was an approximate answer. To answer this question more precisely, it's helpful if we can write a function for the bacteria count in terms of the number of days since Monday at 8 a.m. To do this, it's helpful to look for a pattern. So if we began with a count of 1,500 bacteria, how do we get the bacteria after day 1? Well, what we did is we doubled 1,500. And if we wanted to calculate the number of bacteria after 2 days, we would double 3,000. Or after 3 days, we would double 6,000. Or after 4 days, we would double 12,000. And even if I looked back at the wrong days here, you get the idea behind what's happening. What is the pattern here? Well, our pattern is we double. The pattern is the double. Ooh, and I'm really sorry, I don't know how to spell that, but there's no E. Because D-O-U-B-L-I-N-G. And I'm really sorry, I'm not sure if that's spelled right. Doubling. And then it says, what stays the same? Well, what stays the same is that our 1500. The 1500, what we started with, stays the same. And then our other question is, what is changing in the expression? Well, what's changing in the expression is the number of days. And now that we know that information, I want to slow down here for a second and let you give a chance to get caught up. Now that we know that information, we can use it to help us write our equation for this. And what it says use the pattern from above to write a function p for population that represents the number of bacteria after t days. So this is the population, p parentheses t, means the population after t days. And what happens is, we started with 1500. And then what's happening is we're doubling that. That's our pattern. And what's going to change is the t, the exponent in this case. 1500 times 2 to the t is our function. And it says, check a few values to ensure the function gives you the same data that you wrote in the table above. Well, the way that we can do that is we can go into our calculators, and we can go to y equals. I may have it in there already, and it doesn't look like it. But I'll go back here. And if we type this in, we've got 1500 parentheses 2 caret to the x. And where we can check our values here is we can compare our calculator back to our table. So we can go to second and the graph button, which gets us up to the table function. And as I scroll back up here so we can match some numbers here, if we compare 0, 1500, 1, 3000, 2, 6000, 3, 12,000, 4, 24,000, 5, 48, don't those match our numbers in our table? So we know that we have done this correctly. Now what it says is use the function to determine the number of bacteria present after 3.25 days. Well, we approximated earlier. Now what we're going to do is we're going to take 1500 times 2, and instead of t, we're going to replace it with our number of days, which is the 3.25. Back to our calculator. To get out of this screen, we're going to go to second, and then the button right beside it, which is mode, but it gets us up here to the quit. And now we're going to type in 1500 parentheses 2 caret, and then we're going to type in our 3.25. When we press enter, we get that value, which is roughly 14,270 bacteria. I know there's a decimal point, but can we have part of bacteria? I don't know. Did we overestimate or underestimate with our original guess? Looks like we overestimated a little bit. But we did the best that we could with the information that was given to us. So now as we flip our paper over, what we're going to do is we're going to graph this. And we just typed our function into the calculator, so we know that we have it correct here. But when we graph it, look at that. So what we're going to do is we're going to look at our window here for a minute, and we're going to change it up a little bit so that we have a little bit more realistic picture on here. So window is at the very top of your calculator screen. It's the second value in. On a TI Inspire, you have to go to your menu function to change the window. And I don't need any negative x's because we don't have negative bacteria. I'm going to put 0 there. I left the next two values, the x max as 10 and the x scale as 1, because those will be fine for us. But just like we don't need any negative x values, again, we're not going to have any negative bacteria counts. But if you look at our table, we only did 5 of them when we were at 48,000. So I'm going to change our y max, and I changed it. I played around with this a little bit at home to 10,000. Really, if you want to get technical, you'd probably want to do 100,000 or even 1,000,000. But our picture will show up fine with 10,000. And the scale here I'm going to make is 100. And that's going to give us a little bit better picture. And I'll write that down in a minute in our window section. But I'm going to hit graph. And what that does, at least, is it gives us something that we can look at here that's more realistic. When we draw our picture, it looks something like that. And once again, the menu settings that we use were 0, 10, and the x scale of 1, which is x SCL. And then our y min was 0. I did 10,000, and our scale is 100. Notice, we need to label a couple of key points, including our y-intercept, and we can go back to our table on here, which is second, and the graph that gets us to our table. And most calculators end up here. That's where they start on the screen. And we've got 0, 1,500. That first value there is our y-intercept. So this is 0, 1,500. And we have our table on the screen here, which I'll just put down here in number 8. But the next value in number 8 says 1, 3,000. Put another point on there. 1, 3,000. And you don't have to put 1, 3,000 on there. You might put 2, 6,000. Just one more value there from your screen. But a nice little piece of graphing calculator technology here on number 8. Let's see, did we answer everything on 7? Adjust your window, sketch a graph, label a few key points. Good. Using the graph. And I don't know how to do this for Inspire yet, but for TI-84 users, remember the question. It was 3.25 days. How much bacteria in 3.25 days? We can go back to our screen here. So here's our screen. We can go second and calculate, which is on the trace button. Trace. It gets us up to a calculator button because we press the second. And then we want to do number 1. And what we get down here on our screen is we get x equals, and it's flashing. And what we can type in here is we can type in the 3.25, and when we press enter, watch what happens. Look at that number. Does it look familiar? It's the number that we found at the bottom of the front page. The 14,270 bacteria in the pool on Thursday afternoon. If nothing is done and the bacteria continue to double, how long will it take for the count to reach 3,000 bacteria? Well, first parts first, it says write an equation. So now we know the answer. So there's 3 million. The 1,500, that's what we started with. It's not going to change. And the fact that we double every day is not going to change. So our question says, how long? So we want to know what is that value of time. And we can use our table again to determine that. When we go back to table, we're going to go to second and graph. And we're going to start scrolling. And some calculators only show to 6. Mine luckily shows to 10, but we're looking for 3 million or close to that. So we've got 1,500 on day 0. We've got 48,000 on day 5. At day 9, we have 768,000. But on day 10, we've got some odd looking notation. 1.54 e to the 6. And I'm going to scroll one more there. But I'm going to scan this in here. Because our answer is, when will it reach 3 million? And what we need to know is this notation here. So I'm going to draw an arrow. 1.54 e to the 6 means 154,0,0,0 means that we have 1,540,000 bacteria approximately in the pool. E to the 6 is the scientific notation. 3.07 e to the 6 is 307,000,000. Put my comma in the wrong place because it's 3,070,000. We had to be able to convert that from scientific notation into regular notation. But if we can do that, we can answer our own question. And we probably could have gotten it without. This is 1.54 million. This is 3.7 million. And the question again says, when will we reach 3 million? So our answer is going to be between day 10, which is the 1.54 e to the 6, and day 11, which is the 3.07 e to the 6. Again, something to ponder is that, could you solve this equation that you wrote in problem 9 algebraically? And I bet the answer is yes, or else we wouldn't have put it in there. But so far, what we've been dealing with these early days of this unit is we've been dealing with the equation y equals b to the x. And that was a good place to start. But today's equation, remember, we had 1,500 times 2 to the x. And in general, to write an exponential function that models a real-world scenario, we need 2 things. We need an initial value, which is a. Then our b is the rate at which we grow, or we decrease. And always think of the pattern in terms of what you need to multiply by to get the next number in the list. So as we flip our page here, we're not going to get very far in this problem, but I may try to finish it later on the video this afternoon. But Maria made a half-gallon of fresh orange juice on Saturday evening for Sunday's breakfast. In the middle of the night, Liesel got terribly thirsty and drank half of the fresh orange juice. She replaced what she drank with water, hoping no one would notice. Not after Friedrich woke up, drank half the orange juice, and filled it back up with water. Oddly enough, the rest of the Von Trapp children did the same. By the way, any theatrical people may recognize that as the Sound of Music, children, just in case you're wondering. But if we fill in this chart here, Maria made 64 ounces of orange juice. Then Liesel got up and drank half of it. So now there's only 32 ounces of orange juice. She filled up the rest with water. Then Friedrich got up and he drank half of the orange juice. So now there's only 16 ounces of orange juice left. And then we follow the same pattern. 8 and 4 and 2 and 1 and 1/2. And you might want to put 0.5 in there. Doesn't make any difference to me. But what we have to do is we have to write a function f of x that represents the amount of fresh orange juice left in the pitcher after each time someone sneaks some orange juice and then refills it. So again, here's the key. What is the initial value? What do we start with? We started with 64 ounces. And what's our pattern? Our pattern is each time we're taking half. So when we write this equation, what we end up with is we end up with f of x equals, we started with 64. Our pattern is 1/2, and then we're going to raise it to the x, or the t, but we'll go for x. So as we get close to our time limit here, suppose this pattern, did I skip one here? There it is. Sunday morning, George wakes up early and is so thirsty that he wants to have some orange juice before everyone else wakes up. Using the function from above as well as the table to confirm your answer, determine the amount of orange juice that will be left after George has his fill. Well, what's x going to be in this one? 1, 2, 3, 4, 5, 6, 7. George is 8. So we're going to take our formula there of 64 times 1/2, and we're going to fill in the 8. And when we type that into our calculator, which I'm not going to spend my time doing right at this moment, we end up with the answer of 1/4 ounce. We could type it into our table and look at it there as well. But either way, we will get 1/4. This may be a repeat for people who are watching the video. But Sunday morning, George wakes up early and is so thirsty that he wants to have some orange juice before everyone else wakes up. Using the function from above, as well as the table to confirm your answer, determine the amount of orange juice that will be left after George has his fill. Well, we need to fill in x. And what is x going to be in this particular problem now? Well, he's going to be the 8th person to drink orange juice. So we're going to take our function of 64 times 1/2 to the x, and we're going to put in the value of 8 for x. And when we type that in, we can go to second and mode. That will quit us out of that original function. And now what we're typing in is we're going to type in 64. By the way, if you have the fraction button, you can type in the 1/2. If you don't have it, just type in 1 divided by 2. Make sure to close your parentheses. 1/2 caret to the 8. And when we finish that, we get 0.25, which is 0.25. Depending on your calculator, you may have gotten 0.25 or simply 1/4 ounce. The nice thing is that you can look at this on your table feature in your calculator as well. If we go back to our y equals screen and we clear out that value and we put 64 parentheses, I'll use my fraction button this time, of 1/2 to the, remember, the x comma t comma theta comma n, there's our x, and we can look at the table. The one thing that we needed to know, and we can see it on our screen here, is that it was the 8th person. And our 8th person there also happens to end up with the 1/4. Suppose this pattern continues for 20 people. Will there still be some orange juice left in the pitcher? If so, how much? And use both the equation and the graph to verify your conclusion. Well, the good news is we have our function in our calculator, but now we're on the 20th person. So this is x equals 20. So it's going to be 64 times 1/2 to the 20th. It's going to give us our value for our function. (64) times 1/2 to the 20th gives us that. Unfortunately, we've seen that notation already today. But what that means here, this one is 6.1035 times 10 to the -5. So what we do in this one is we're going to take our decimal point and we're going to move negative. 1, 2, 3, 4, 5. And we'll fill in these blanks here with 0. This is 0.0000610 0, 0, 0, 0. I lost one of the zeros. 6, 1, or so. If we look at it on the table, it may be that it's in fraction form, but second and graph gives us a table. We're on the 20th here, so you can probably get there faster than I. But notice, we get that 6.1 e to the -5, so there it is in table form as well, meaning the same thing. So will there still be some orange juice left in the pitcher? Technically, yes. If you poured yourself a glass of orange juice, would you taste any orange juice? You probably wouldn't change any orange juice. So lastly, suppose this pattern continues infinitely. Will there always be orange juice left in the pitcher? Technically, yes. But it will be so small of an amount that we won't be able to taste it. Or taste any.